Dear students, in the last lecture we have seen Lambert's law, Beard's law, and the combined law, that is Lambert's-Beard's law, and a deviation of Lambert's-Beard's law. In today's lecture, we will see the instrumentation part. So the first point is instrumentation for absorption spectroscopy. So in this point, there are two points are included here: the single beam photoelectric colorimetry and double beam photoelectric colorimeter. So now see here, the absorption of radiation, by absorbing media like solution is quantitatively measured by using photoelectric colorimeter and spectrophotometer. So in these instruments, that is by use of this photoelectric colorimeter or spectrophotometer, we are going to determine the concentration of the absorbing solution. So what happen in these instruments? These solutions absorb radiation of suitable wavelength and they gives readings depending upon the amount of compound in the solution. The instruments used in spectroscopy are broadly classified as photoelectric colorimeter and spectrophotometer. Colorimeters works in the visible region, while spectrophotometer can be used in UV visible and IR region. Now see here, colorimetry instrument, it only works in the visible region, while the spectrophotometer can be used in the UV region or in the visible or in the IR region also. Colorimeters are generally used for quantitative analysis of colored compounds which absorb visible light. So those solutions which are colored, for such solutions only the colorimetry can be used. Spectrophotometers are used for determination of structure of colorless as well as colored compounds in addition to quantitative analysis. So the spectrophotometry is used for the analysis of colored and colorless solution, but the colorimeter is used only for the determination of concentration of colored solution by use of visible radiation. Photoelectric colorimeter, so now see here, photoelectric colorimeters are of two types. So there are two types of colorimetry: the single beam photo colorimeter and double beam colorimeter. If you come to see here, that there are two types of colorimeter are there: single beam and double beam. Now see here, what is the difference in between these two, single and double? The single beam spectrophotometer, in which one optical beam, so only one optical beam is used here. The blank, that is a solvent, has to be replaced by the sample for the measurement of absorbance. So in case of this single beam colorimeter, we use only one optical beam, so that after calculating the transmittance or absorbance of this blank, that is solvent solution, we can replace it and we can use now sample for the measurement of absorbance. So in case of single beam colorimeter, we use only one optical beam. But now see here, in case of the double beam colorimeter, in which two identical optical beams are provided. So in double beam, two identical optical beams are used. One beam passes through the blank and the other simultaneously passes through the sample. So we use, in case of this double beam spectrophotometer, we use two identical optical beams, but while in case of single beam colorimeter, we use only one optical beam. So in case of this double beam, one optical beam passes through the sample and another passes from the blank, that is solvent solution. The optical beam coming from the source of radiation, now see here, whatever the radiation which is coming from the source is divided into two identical beams and which passes through the solvent and sample at the same time. So in case of this double beam spectrophotometer, the optical beam coming from the source is divided into two identical beams, and one beam passes through the solvent, another passes through the sample. Uh, so this is the major difference between the single beam colorimeter and double beam colorimeter. So now we will go ahead. The next point is single beam photoelectric colorimeter. Just we have seen in single beam colorimeter only one optical beam is used. So now see this figure here. We are using a source of radiation. Collimating lens are used here, and the color filter is also there. And now we are putting the sample holder in between the source of radiation and the photocell. So in between the source and the photocell we have a sample holder. So the light radiation passes through the sample holder and it incident on the photocell, and finally a reading, that is a colorimeter is there to read, that is percentage of transmittance and absorbance of the light radiation which is coming from the sample holder. So now see here what happened exactly in the single beam photoelectric colorimeter. In a single beam colorimeter, a narrow band of wavelength is incident. So we are using a narrow band of wavelength which is incident on an absorbing sample. The absorbance or percentage transmittance of the sample is determined after adjusting the absorbance of the solvent to 0 or 100% transmittance for the same band of wavelength. Now what we do first, in a sample holder we are taking a solvent solution. So we are using a solvent solution as a blank, and through this solvent we are passing a narrow beam of radiation. So when it passes through this blank solvent, it comes to photocell and it incident on the colorimeter, and we are going to read the transmittance and absorbance. So when we are using a solvent, we must adjust the absorbance of this solvent solution to 0, because in the solvent there is no any another ions or another sample which is dissolved in the solvent. So the solvent is free from compound, therefore when the radiation is passes through the solvent, whatever the light is emitting or it is coming outside or transmitted, the absorbance of that sample should be 0 and transmittance is 100%. That is, the source of radiation is totally transmitted from the sample, from the solvent. There is no any absorbance for this solvent. So all measurements are done using a single optical path for the beam of light. So in this case we are using only a single beam of light, and that is passed through the solvent solution and sample solution. When it first passes through the solvent, the absorbance should be 0 or the transmittance of that sample should be 100%. Now see the points which are explained here. A photoelectric colorimeter has the following components. So just I explained you, that is there is a source of radiation is there, color filter is there, lens is also used for the filtration of that wavelength of radiations, and photocell is there, and lastly digital reading is there. So now see the first point of this component, a source of visible light. So from what is the source of that light then? A source of visible light, that is an incandescent lamp with a tungsten filament is used for the source of radiation. So in this case we are using a tungsten filament as a source of visible light. The filament on electric heating emits visible radiation. So after electric heating, it emits the visible radiation by the tungsten filament, and it comes through the collimating lens, and these lenses are convex lens. The second point, now we are using a color filter as a component for this single beam photoelectric colorimeter. Now see here, what is the use of that color filter? A color filter which selects a narrow band of wavelength which enters a fine slit and is then incident on the sample. So by use of this color filter we can select a narrow band of wavelength. A third one, a sample holder called as cuvette. So you all did the experiment in the FYBSc in the practical. So you know what is meant by cuvette. It is a sample holder. It is a rectangular transparent container of a glass or quartz. A sample holder in test tube form are also widely used for this analysis, and most sample holders have a standard path length of 1 centimeter. So the sample holders are like this. Now see here, just I will show you how the sample holder looks like. So this is a cuvette. So in that we are using a solvent or sample, and that cuvette is put in between the source of radiation and photo cell. The fourth component, that is a photocell, or it is also known as transducer. So now see here what it did. A photocell which converts the transmitted beam emerging from the sample into an electric current. So the role of photocell is to convert a beam into electric current, and this electric pulse is due to the emission of electrons from the photoelectrode surface caused by the transmitted beam falling on the photoelectrode. So in photocell, on the wall of photocell there are photoelectrodes are there. When the light is coming from this that is the light, whatever it is transmitted from the sample, it is incident or it strikes with the photoelectrodes, and because of that the electron pulse is emitted, and that creates a electric current in the photocell. Now fifth, that is a readout system like a dial to directly read absorbance or transmittance T of a sample. The readout system is needed because, now see here, the electric current from the photocell has to be converted into the absorbance or percentage transmittance of the sample. So why the colorimeter dial is used here? So this dial converts a electric current into the absorbance and transmittance value. So these are the 5 components are used in the single beam photoelectric colorimeter. So how it works now, I will explain here. Now see the working. The cuvette is first filled with the sample, so it is filled with the solvent. So the first case is that you should rinse the cuvette, or you should wash it completely by use of solvent, and after that you have to fill that cuvette with the solvent and measure the transmittance of that solvent by putting into the in between the color filter and photocell. So in this case, when we put the solvent in the cuvette and it is put into the sample holder, then when the light is passing through this solvent, there is no any absorbance of the radiation, because in the solvent there is no any compound. Therefore, whatever the light is incident on the solvent, it completely goes to the photocell. Therefore, there is no any decrease in the intensity of radiation, or there is no any absorbance. Therefore, absorbance for the solvent is 0, that is the transmittance is 100%. So by use of this Lambert's-Beer's equation, now see here, A is equal to negative log to the base 10 T. So we have a value of transmittance. By putting the value of T, we can calculate the absorbance, or A is equal to negative log to the base 10 T, and this also we can use this equation. A is equal to epsilon C into L. So C is the concentration of the solvent and L is the path length of the sample. The calibration curve method is generally used to determine the concentration of the sample solution. So by use of this calibration curve method, we can easily determine the concentration of the sample solution. So this is the simple single beam colorimeter is here. So we have just seen what are the source of radiations, what is the source of radiation, what are the components of this instrument, and how the light is get transmitted from that solvent, and how the light is, why the light is absorbed by the sample solution. So these are the detail of these components, yeah, you have to go through this. Just I have explained you, but for the more reference you should go for this point. So detector is also is a photoemissive cell is there. Just now see this photoemissive cell diagram. The next we may also use PMT, that is photo multiplier tube we can use. So in that, now see here what exactly photo multiplier tube works, how it works. So this photo multiplier tube consists of an evacuated tube in which several diodes are used. Now see here, see this black half circle like spots are there in the diagram. So these are nothing but diodes which are coated with the cesium metal. So these diodes are put or applied with the increasing positive potential. So when a beam which is transmitted from the sample, it emits a primary electrons from a photocathode coated with the cesium. So at first what it did, when the light comes from the sample or solvent, it emits a primary electrons in the first diode, and then it goes on multiplying on the secondary electrons. Then it goes to third diode, again the electrons are get multiplied. When it goes to 4th, 5th and 6th, it goes on multiplying. So therefore whatever the primary electrons which are generated in the first diode, they are get multiplied in several times at the last diode. So at the last, what happened, this process is repeated at the successive diodes to which increasing positive potential are applied. So why the electrons are get multiplied? Because we have arranged these diodes with the increasing positive potential. So more the positive potential, the multiplication of electrons get more. So million times greater than, so whatever the current, output current is there, it is million times greater than the primary current which is produced by the cesium photocathode. So now the amplified current is received by the collector electrode, and finally that is this instrument converts the electric current into the absorbance and transmittance value. So this is a photovoltaic or barrier layer cell, can also be used for as a detector. So this is what we have seen, how it works, single beam photoelectric colorimeter, its components and how it works. Now the second next is a double beam photoelectric colorimeter. Just in the last just before 15 minutes we have just seen what is the difference between the single beam and double beam colorimeter. So in single beam only one optical beam is used, but in case of double beam colorimeter we use two identical optical beam, and one beam passing through the blank and another passing through the sample solution. Now see this instrument, that is figure 8, double beam photoelectric colorimeter. I will explain just within 5 minutes how it works. Now see this figure. At the left hand side, source of radiation is there. It is common with just like single beam. A lens are used, color filter is also used, sample cuvette is there, photocell is there, and finally now see this extra extra figure. What is in that? Now see here, whatever the light which is source of light which is coming here, it is gets splitted into two beams. Just now see these two parallel lines at the color filter. So one goes through the sample cuvette and one goes to the blank cuvette. So mirror is used to reflect that light to the blank. So two parallel identical beam of light, one goes through the sample cuvette and another goes through the blank cuvette. Now see here, just I will explain a beam of visible light from an incident tungsten lamp. So the source of radiation in this case is a tungsten filament lamp is used, and it is passes from a colored solution. Just wait. See here. So in case of this double beam photoelectric colorimeter, a beam of visible light from an tungsten lamp passes through the color filter. So this color filter selects a narrow band of wavelength. So the role of color filter is to select a narrow band of wavelength. A mirror that splits this narrow band into two identical beams. So what it did, so now a mirror splits this narrow band into two identical beams. So one passing through the sample and another passing through the solvent. So the light is now split into two beams, one passing through the sample and another passing through the solvent. Now see here, in the solvent there is no any compound, but in the sample solution there is a compound. Therefore the sample absorbs a part of beam whereas solvent transmit it completely. So the light passing through the solvent is completely transmitted, but the light passing through the sample is some amount of light is get absorbed by that sample solution. The two beams then fall on the respective photocell. So the light which is transmitted from the solvent and the light which is the light beam which is transmitted from the cuvette, that is blank cuvette, they both respectively fall on the photocells where photoelectrons are emitted. The two electric currents thus produced here. So the first beam of light which is transmitted from the solvent, it emits certain amount of electrons, and the another light which is passing through the solvent, it also emits certain amount of electrons into the photocell, and therefore due to the emission of these electrons some amount of electric current is generated, and this two electric current thus produce a resistance here. So the solvent, the beam which is passing through the solvent and the beam which is passing through the sample, these two different beams that is produces variable resistance. So now see here a resistance AB. So a resistance AB for the current coming from the solvent, and the resistance CD, the current coming from the sample side. So these two resistance are produced here. A potential gradient is developed now. So now see here, due to difference in potential because of these two different beams, after passing through the respective sample and solvent, there is a potential gradient is developed across AB and CD. So AB is calibrated to read percentage transmittance. A galvanometer connected across the two resistors serve as the null indicator. So now see here, in between these two resistors, a galvanometer is used. So when there is a difference in potential between the two lights, which are two beam of light which are coming from the sample and solvent, then the galvanometer shows some readings. If there is no difference in the potential between the two beams which are coming from the sample and solvent, then there is no any absorbance of light. Therefore now see here the last two lines. When the potential at the contact between AB and CD are equal, means there is no any absorbance by the sample solution, no current flows in the galvanometer, and hence there is no deflection in the galvanometer. So this is the basic explanation for this double beam photoelectric colorimeter. Now how it works, it is similar, it works similar with like a single beam colorimeter. Just the difference is that in the double beam colorimeter we are using now two identical beams. One is passing through the sample and another is passing through the solvent solution. Now see here working, the solvent is first taken in both the cuvette jockey J1. Now see here, in between A and B there is J1, in between C and D there is J2. Jockey J1 is set at point A and J2 is adjusted along CD till there is no current flows as indicated by the null. So this J1 and J2 is adjusted like that. There is no any that is fluctuation or indication in the galvanometer. The sample is then placed in the sample cuvette. So by putting the sample in this sample cuvette, this sample absorbs a part of light and the transmitted beam emerging from it falls on the photocell. So some amount of radiation is absorbed by the sample solution, and whatever the amount is remaining, it is transmitted and that falls on the photocell. This beam has less intensity, that is, the beam coming from the sample has less intensity than the beam coming from the solvent. Hence, there will be a proportionate decrease in electric current produced in the photocell. The voltage across CD decreases. As a result, the null in the galvanometer is now disturbed, and now jockey J1 is moved along AB to a lower value so that null is restored. The percentage T, that is transmittance, is directly read on the scale when the null is restored. So due to fluctuation in the electric current at the resistance AB and CD, the galvanic cell shows an indication, and to restore that galvanic cell reading, the jockey is moved along the AB, and because of that the transmittance is directly read on the scale when null is restored. So this is a simple working. If there is an if the sample absorbs an incident radiation, then there is change in the potential gradient across AB and CD. Due to change in potential, there is a change or disturbance in the fluctuation in the galvanometer, and because of that we are going to determine the transmittance value. Now see the last 3 points. Double beam photometer have several advantages over single beam. What is the advantage of this double beam on the single beam? Now see here, first one, changes in the intensity of incident light. Now see here, change in the intensity of incident light due to voltage fluctuation in the power supply are compensated by splitting the incident beam into two identical beams by use of mirror to balance the photocell. So suppose there is a fluctuation in the power supply, but though there is fluctuation, it does not affect the working of this double beam spectrophotometer. But in case of the single beam spectrophotometer, we are using only a single beam in that single beam colorimeter. Therefore, if there is a fluctuation in the light, then it leads to the fluctuation or difference in the reading. Second one, the readings are not affected by changing the sensitivity of photocells or galvanometer, as null method is used here. So in double beam spectrophotometer, we are using a null method, and if there is change in the sensitivity of photocell, there is no any change on that method. The third one, the scale readings of the instrument are linear with the concentration of the sample solution. That is, if there is a change in the concentration of the sample solution, then it directly gives us the difference in the reading, that is transmittance. Therefore, the double beam spectrophotometer is more advantageous than the single beam photometer. So this is what we have just studied in this lecture. So how this absorption spectroscopy works, what is the difference in single beam colorimeter and double beam colorimeter, what are the components of the single beam colorimeter, how it works, then the double beam colorimeter working and its explanation. So in double beam colorimeter, we know that the visible light is split into two equal identical beams, and one is passing through the sample and other is passing through the solvent, and After that, we calculate difference in the potential at the galvanometer, and by use of that we can calculate, or we know the readings of transmittance and absorbance. By use of that we can easily calculate quantitatively the concentration of colored solution in case of this single and double beam colorimeter. Thank you.